Our next speaker is Elisabet MARTÍNEZ SANCHO from WSL in Switzerland. And she's going to present some of the first results that are coming from the large effort in producing the endocrinological data that has taken place in GenTree.
Thank you for the nice introduction. So today the talk is going to be about tree growth sensitivity to climate change. And this talk is going to be split in two parts. So the first part will be to assess how the tree responses are within the climate space of a species. And the second part will be to assess how site characteristics can modify these expected patterns. So first of all, the climate space consists on the multidimensional climate conditions where a given species occurs. If we look at the map in the left, we have temperature and precipitation, and the green area corresponds to the combination of both that allow that a species exist. However, in the context of climate change, the climate space of the species is moving towards warmer and drier conditions, which means that some populations will face novel conditions for the species, so these ones here. Others will be still in the range of the climate conditions of the species, the ones in the middle. And there are some climatic conditions that will disappear of the current distribution of the species, but they may appear in our part of the world, so these ones here. But populations may persist depending on the species' climatic sensitivity or the adaptive capacity. For this reason, we believe that endocrinology is a powerful tool to assess the tree climate sensitivity, because the growth of any organism is controlled by the most limiting factors, and these factors can change over time. Since climate is the most important driver of the interannual variability of the tree ring series, we can track how these factors, or the limiting factors, are changing over time. And if we think in the climate sensitivity of the species within the context of the climate space, we think that, or we expect, or we hypothesize that tree growth of populations located in the cold and wet parts of the space will be limited by energy. So these are the ones that could still benefit from climate warming. But tree growth from populations that are located in the dry and warm part of the climate space, these will be limited by drought. So we have a duality in the climate response to climate change. However, we know that some biotic and abiotic effects can modify these expected patterns, for instance, competition and soil characteristics. In the case of competition, in a low density stance, there is higher water availability, so we will find deviation of the expected patterns. And in the same case for soil characteristics, so when there is deeper soils or soils with better structures, there is a better water retention capacity. So in both cases, we will expect deviations for what we expect. This is well acknowledged in the dendrochronology community, and there are already papers acknowledging or mentioning these effects. However, there is no global study assessing these impacts, basically because there is no data available. So the main of this talk, or the aim of this talk, is to assess how climate space can predict tree growth responses to climate change. And we will do that for 4 of the most important tree species in Europe: spruce, beech, oak, and pine. And as I mentioned, we split this talk in 2 parts. So the first part is to see how tree growth sensitivity can be predicted by the location of a population within the climate space. We want to see also if there are differences between species or among species. And then we will see how site characteristics can improve or not our models. So first of all, we need to define what is climate space. To do that, we use high-resolution tree occurrence data. So in this case, we use a spruce. And for all of these points, we extract the climate conditions to plot the climate space. It's important to notice that we are going to focus only in summer conditions because this is most stressful period for tree growth. And also we assume that trees in all the continent are growing during this period. And once we obtain our dots, so basically, as I said, each point we transform it to the climate conditions, we can define what we consider the climate space, this red line. So basically we jump from the geographical space to the climatical space. Now afterwards we need to collect tree ring data. And as Santiago mentioned, we have the tree ring data from the GenTree sites, but we combine it with the data from the ITRDB, which is the International Tree Ring Data Bank. As you can see, we nicely cover the distribution area of the species, so assessing a large part of the spatial heterogeneity. But our data also has temporal heterogeneity because it's a time series. I'm not going to go into details how we analyze or which analysis we use to analyze our data, but I will try to really simplify. So first of all, we need to apply what we call the trending, so removing age and disturbances to keep the interannual variability of our series. And then we apply a novel approach. So basically, we rearrange all the rings to make it easy. The upper part is the normal tree ring series, so all the rings are organized by the time scale, which means this year is 1956, this year is 1957, 1958, and so on. So basically what we do here, we reshift all the rings and we arrange them by the water balance, which means that the ring that was here, now it's here because it has the higher water balance. And this ring that was here, now it's here because it's the year that has the lower water balance. Once we have all our rings on our new time series, we calculate Picea correlations between this new series and summer temperature. And we do this for the period 1960 to 1990, because there is a period where there is a higher overlap between the ITRDB datasets and the GenTree, but also is a period where there is a higher increase in temperature. Why do we do that? So first of all, we increase our number of observations. If we have 200 sites, now we have 2,000 observations. And we also assess how the population adjusts to warmer and drier conditions, because we calculate moving correlations. Once we have our map, our climate space, I don't know if you can see the red line here, we put inside all the correlations that we calculated for all the sites in all the 20 years moving correlations, and we put it in the context of temperature and precipitation, in the context of climate space. Here we use linear mixed models to calculate how we can predict the correlation between tree growth and summer temperature. And once we have our model, we obtain a continuous layer of predictions. And we do our game here. So we have the climate space, and we change to geographical space. So it means that, I don't know if you can see the maps, but the red areas of the maps correspond to the red areas of the climate space. And the blue areas of the map correspond to the blue areas of the climate space. I will go later in details. And after this, the second part of the talk will be to see if the effect of competition and soil characteristics can modify our patterns within the climate space. And we can do this only with the GenTree sites because we don't have data available for the ITRDB sites. So these are the first results. Here we have the climate space of the 4 species, and we see that they overlap in some areas, but there are some areas that the species are unique, meaning that they are more competent in this kind of climate. And then when we have our areas, we plot, or we plot our predictions of correlations between tree growth and summer temperatures for the 4 species. What we easily see is that the 4 species show similar patterns, which means that, as we expected, populations located in the cold and wet parts of the space show that tree growth is positively related with summer temperatures, meaning that they can still benefit from global warming. Whereas populations located in the dry and warm part of the climate space the tree growth have a negative relationship with the summer temperature, meaning that those are suffering the consequences or the impacts of climate change. And taking in consideration that this is a continental scale study, our models predict a quite large part of the variance, growing from 20% in the case of pine to almost 40% in the case of beech, only taking in consideration climate conditions. Now we do our game and we jump all these climate spaces and we map the geographical space. It's important to notice that here we are not plotting the distribution area of the species. We are not saying that there is beech growing in high Finland. What we are saying is the climate of Finland during summer might be suitable for or falls within the climate space that we define. But maybe winter conditions are not suitable for the species, but we are not accounting for this yet. So the first thing what we see our maps is that large part of the maps are red, meaning that the prediction says that tree growth is negatively related to summer temperatures. So these are suffering the impacts of climate change. If you put a threshold of the correlations at minus 0.1, we see that in the case of beech, almost 70% of the climate space will have this negative relationship with summer temperatures, which is a large part of the geographical space. And to pine, we have 5%, but it's important to notice that maybe the correlation is a bit higher. It doesn't mean that it's positive. We only find positive relationships in the part of Scandinavia. But I want to say also that this is not a latitudinal effect, because if I zoom in Switzerland, which is a country with a large contrast, we see that a difference in altitudinal scales, meaning that in the low valleys, we still have this negative relationship between tree growth and summer temperature, but at high elevations, we find a positive effect. And now I'm going to just briefly explain the last part of the talk. So we have the same model, but plotted or represented in a different way. And now we're going to account for the effect of competition and soil characteristics. So here we have summer temperature, which is predicting the relationship between tree growth and summer temperature. And then we have two sides, one wet and one dry. In low summer temperatures, we see that the tree growth has a positive relationship with summer temperature, meaning that it's still fine, this temperature, they are still doing well. If we go to higher summer temperatures, we see that the dry side is suffering more than the wet side. This is also what we expected before. Now we are going to include the effect of competition. And then we see that the patterns are almost similar, especially in a higher temperature, so the dry side is always suffering more than the wet side. And the variance explained increase when we add competition. And also it's important to see the effects. So when we add competition, the sites with high competition, the correlations are lower because they are competing for the water resources, also as expected. This is the case of oak. Now we are going to do the same for the 4 species. So if we go for spruce, first of all, spruce and oak, we see the same pattern as I mentioned before. So dry sites always suffer more with high summer temperatures. And then when we add competition, in the case of spruce, this effect is not so evident, but still, when there is high competition, they suffer more, and the same in the case of oak. And also, the variance explained by the model is higher. But in the case of pine and beech, it's not that clear. So the model, the variance it's lower than in the case of only climate conditions, and the patterns get a bit blurry. So it's not easy to distinguish anymore the effect of wet and dry. And now we do the same for soil depth. The upper plot is exactly the same than before. It's just to compare. But now in the lower part, we include the soil depth effect. What we see in the case of spruce and oak is that when there is a deep soil, so meaning that there is more water retention, the correlation are slightly higher, especially in the case of oak. So they suffer less because there is more water. In the case of pine or beech, this effect, again, gets a bit blurry and not clear patterns anymore. And the variance explained it's slightly better, but we remove what we wanted to see, which is the effect of the dry and wet. So to conclude, we found strong patterns in tree sensitivity within the climate space. Basically, and contrary to what was mentioned this morning, not all the trees are benefiting from climate change, so tree growth from populations from wet and cold environments are the ones that are benefiting from the increase of summer temperature. But the ones that are growing in the dry and hot parts of the climate space are already suffering the impacts of global warming. However, when we plot this in the geographical space, we see that most part of this geographical space falls into this red area. So most of the geographical space is already showing a negative relationship between tree rings growth and summer temperature. And then last, but when we add the effect of competition and soil depth, maybe we can improve the explanatory power of our models, but but the trends of the most significant trends don't change that much. And before I finish, if you want to know how we measure the tree rings in the GenTree sites, please don't forget to visit the poster of Lenka Slamova. She will show you the awesome job that she did. And if you want to zoom in into the tree rings and understand boot anatomy, also visit the poster of Patrick Fonti. And thank you so much for your attention.
Thank you, Elisabet. We have time for one question.
Yeah, thanks very much for the talk. It was very interesting. I was wondering, how did you select the variables for defining your climatic space? Because, for example, you talk about these summer temperatures. Why didn't you choose the cold temperatures or other limiting factors?
Yeah, we use summer temperatures basically because we know that the tree rings have a strong signal of a summer temperature, either positive or negative. And also what we assume is the most stressful period for growing vegetation. So we assume that in further climate conditions, this will be the most stressful period for the trees.
And in southern populations? In southern populations?
In southern populations, I mean, yeah, it could be other periods, but we choose summer. Because it was also tricky to decide which period we should take, because common growing season is not the same in the latitudinal scale. So that's why we keep only in the summer period.